Okay, welcome to FSO 703 and your second lecture with me, Dr. Wightman, carrying on from where we were last time on solutions. I've obviously made a big impact because it's so popular. I've got 5 recorders today to record what I'm saying, so I'm feeling a bit like a pop star having so many people interested in what I have to say. The coursework is now on Blackboard. Hopefully you've found where it is under module assessment, and 1 or 2 people have started to have a look at it. Some of the questions you may not be able to answer until later weeks when we've covered the topics in the lectures and in the tutorials. Bear in mind that if you click submit, you will actually submit what you've done so far. You can save what you've done, the questions that you've done. You don't have to do it all in one go. But if you click submit, it will actually submit the work you've done. If you do that by mistake, then please let me know and we'll see what we can do to reissue the work to you so you can have another go. Has anyone had encountered any problems looking at it so far? I know it's early days, but if you do encounter any problems with it, then please let me know. It's the first time we've done it online, and it's possible there may be glitches in the program that we haven't been aware of. Hopefully we've ironed them all out, but sometimes it's very specific in the format that an answer has to be, number of decimal places, and whether it's in normal notation or scientific notation. So do check what the question is asking for, and whether it's asking for units or not, because the computer will actually take down exactly what you say. If that doesn't exactly match what the computer thinks the answer is, it marks it wrong, even though your answer to you may be correct. It might be you've included too many figures or not enough figures, so do just check on that. But as I say, if anyone encounters any problems, then please let me know. The deadline for submitting it is week 6, so we've got another 3 weeks after this one to complete it, and we'll release the marks to you the following week. At the moment we've scheduled that for the Friday of that week, but if for any reason we can get things checked earlier than that, they may be released earlier. Basically the computer will mark them, but because it's the first time we've done it, we want to check that the computer's marking correctly. As I say, sometimes odd things happen and it marks answers wrong that are right, and so we want to have a look and see that it's not making any incorrect assessments of your marks before we actually release the grades. So rather than getting your marks straight away when the quiz closes, you'll have to wait a few days before we can do that for you. Okay, last time we were looking at solubility and precipitation. We started off looking at why things dissolve, and relating it to the properties of water, the polar molecule H2O, and the fact that it's polar has a positive end and a negative end of the molecule, and so it will tend to be attracted to other polar molecules, so it'll be attracted to organic molecules, and similarly ions can be attracted to water molecules, and soluble ionic salts, the ions are at a lower energy when they are surrounded by water molecules than when they're in their solid lattice, and the charge of the ion is spread over a larger volume, and the ions then can become mobile, and we've got an electrolyte, a solution that will conduct electricity. We had a look at the solubility rules and why certain materials are soluble, certain ones aren't. Generally, the single-charged ions tend to produce soluble salts, so sodium, potassium tend to produce soluble salts, Other elements from group 1 also produce soluble salts. Likewise, at the other end, the halogens, group 17, tend to produce soluble salts, although there are one or two exceptions, and we had a look at those exceptions. Similarly, strong acids tend to produce soluble salts, hydrochloric acid, nitric acid being the common ones. Sulfuric acid, a lot of sulfates are soluble, but again there are one or two exceptions that we had a look at last time. And then we were using those rules as a means of predicting whether precipitation would occur if we mix two solutions, and also choosing what compounds to use if we want to produce a particular insoluble salt. That might be in the environmental area where we want to precipitate out a contaminant from water and reduce it to as low a level as possible. It might be that we want to produce a particular compound. I was mentioning the example of lead chromate, which is the yellow coloration on lines alongside the road. So if we want to do that, we need to have two soluble salts that we can mix to form an insoluble salt. And we're moving on to have a look at equations for precipitation. You may think, well, it's fairly obvious. Yes, a lot of this is obvious, and probably going over things that you've covered before. I think that's everyone. Is anyone not signed register? Okay, thanks. We're probably all familiar with writing molecular equations where things are in the molar ratio that they are going to react. Remember that we're dealing often with ionic materials rather than molecular materials. They're held together by ionic bonding rather than covalent bonding, but we still write the equation as a molar ratio in the equation. So if we've got silver nitrate and sodium chloride, well, nitrates are soluble, so we'd expect silver nitrate to be soluble. Sodium salts are soluble, as are many of the chlorides, so sodium chloride is soluble. When we mix them together, the silver and chloride ion can combine and form an insoluble silver chloride salt. Silver is one of the exceptions to the rules for the chloride, so that will precipitate out. And if we're writing it in full, we'd put the state of each of these, that it's in aqueous solution, and the silver chloride as a solid. That's probably the way we're most familiar with for writing them. What's actually happening in solution is that each of those compounds is present as separate ions, and those ions are not necessarily attached to one particular ion of the opposite charge. They're mobile within the solution. So the silver nitrate is going to separate out into silver ions and nitrate ions. Similarly, the sodium chloride is going to separate into sodium ions and chloride ions. So on the left-hand side, when we mix those two solutions together, we've got 4 separate ions, 2 cations, 2 anions. But the reaction is going to the right because 2 of those ions will combine and form silver chloride, which is a solid, and the sodium and the nitrate ion in solution, in aqueous solution. So we've shown all the components there in the form that they will actually be in solution, and we've written a total ionic equation. Some of those ions aren't actually doing much. They're there as spectator ions, not taking part in the reaction, and it would be possible to omit those and produce a net ionic equation. It's a net ionic equation because it's only showing the ions that are actually reacting and the ones that are taking part in the chemical reaction. So the only ions that change from one form to another are the silver ions and the chloride ions, and they combine to form insoluble silver chloride. So we've got a much simpler net ionic equation. That can be useful. It doesn't really tell us what reagents we've used, so it has its limitations as well. But if, for example, we were wanting to produce silver chloride and we decided that was the net ionic equation, we could then start thinking, well, how do I get silver ions into solution? How do I get chloride ions into solution? What spectator ions will I need to be available for them to be soluble to mix? The net ionic equation leads us on towards solubility product and calculations on solubility of insoluble or sparingly soluble materials. We've got an equilibrium between the solid and the ions in solution. Previously, in the precipitation reaction, we had silver ions plus chloride ions going to silver chloride. If we've got solid silver chloride, there's an equilibrium between the solid silver chloride and the ions in solution in the water. And we can write that as an equilibrium reaction. Now, when we've got an equilibrium, we've got two reactions going in opposite directions. We've got solid silver chloride dissolving into solution, but we've also got a reaction of going the other way of silver ions and chloride ions combining to form solid silver chloride. When we've got equilibrium, we've got the two rates occurring at the same rate. The rate of reaction going one way is equal to the rate of reaction going the opposite way. If they aren't, we're going to get a change in the amount of material on either the left-hand side or the right-hand side until eventually we reach an equilibrium. So it might be initially that the rate going forwards is faster, taking place at a greater rate than the rate going backwards, and silver chloride is dissolving. Conversely, if we were mixing silver ions and chloride ions in solution, initially we'd be precipitating material until we reached an equilibrium reaction, and then at first the reaction would be going predominantly this way, but very quickly we'd reach an equilibrium between the two. We'll do more about rates of reaction next semester and next year, looking at rates of reaction. But basically the rate is given by a constant, the rate constant for that reaction, and the concentrations. Now, although we call it a rate constant, that constant does depend upon temperature, and the rate constant can be a different value at a different temperature. But normally we're working at laboratory temperature, and so it is a constant under the conditions we're normally operating under. But it means that if we raise the temperature, materials become more soluble because the rate constants change and the equilibrium gets displaced. So we can write the rate going one way as being a constant. We tend to use K for constants rather than C, and we use little k for rates and big K for equilibria. So it's a constant, which we'll put a little f for to show it's forward reaction, multiplied by the concentration of the solid silver chloride. We can do the same for the reaction going the other way. It's a constant Kb times the concentration of the silver ions and times the concentration of the chloride ions. So the rate depends on both the concentration of the silver ions and the concentration of the chloride ions as well. Now, I was saying that at equilibrium those two rates are equal, and so we can equate those, and the rate forward is going to be equal to the rate backward. And so we can write K forward times concentration of AgCl is K backward times concentration of silver ions, concentration of chloride ions. A bit long to be writing that out each time, and we tend to use the shorthand for concentration or activity. And saying concentration or activity, that will become apparent, the difference between them in a few minutes. But if we use square brackets as a shorthand for the concentration of silver chloride, we can replace the words by putting square brackets around it. We get Kf times square brackets AgCl is K backwards times square brackets silver and square brackets chloride ions. We just do a little bit of rearrangement on that. Kf and Kb are constants, and the concentration of silver chloride is constant. As solids are conventionally taken as a concentration of 1. We have to define some standards for concentrations. Similarly, for gases, we take the pressure as atmospheric pressure, 1 atmosphere pressure, as being unit activity. For solutions, we take the concentration in moles per litre. But the concentration of the solid silver chloride, in effect, isn't going to change. Kf and Kb are not going to change because we're keeping the temperature constant. So all of these are constants. One constant multiplied by another constant divided by a third constant. We can replace that by a single constant, which we call the equilibrium constant, K, big K rather than little k this time because it's in equilibrium, and using Sp as the suffix to show it's the solubility product. We'll often use different suffixes for different equilibria to remind us what particular equilibrium we're looking at. We've got Ksp is square brackets silver times square brackets chloride. And it's basically the product of the ion concentrations. That works quite nicely if we've got a one-to-one ratio of ions. If we've got ions with different charges, so we've got a 1 plus and a 2 minus, or a 2 plus and a 1 minus, or 2 and 3, 1 and 3, then it gets slightly more complicated. We can write the net ion equation for the equilibrium as calcium hydroxide solid going to calcium ions in solution, hydroxide ions in solution. But we've got 2 OHs for every 1 calcium. It's a 2-to-1 ratio because the OH is single minus, the calcium's 2 plus, it's group 2. So we could write it as going to calcium plus OH plus another OH. And we're simply multiplying the concentrations together, so calcium times OH times OH, and OH times OH is OH squared. So we've got the calcium times the hydroxide squared is the solubility product. And you'll notice we've got the same power here as we had for the suffix here, the ratio of the ions in the compound. So we've again got a fairly simple expression for the solubility product, but it's slightly more complicated because of this power here compared with the 1-to-1 ratio that we had there. We can look up values of Ksp We could measure them if we wanted to. Some people do. Normally we don't need to. But we can look at values of KSP, and we can use that to work out solubility of ions under different conditions if we want to. And some of the questions in the tutorial are looking at that. We talked last time, was it last time, or was it later on this one? The effect of, no, I think it's later on this one, the effect of different concentrations of ions. And we'll see how we can affect solubility by varying the concentration of the ions. But KSP values are for concentrations in moles per litre for the reagents. As a general guideline, the smaller the value of KSP, the less soluble the salt. Now you have to remember that 10 to the minus 10 is smaller than 10 to the minus 8, even though 10 is a bigger number than 8 when you're getting to negative powers. So you just have to stop and think a little bit which is the smaller number. I say in general, that certainly applies if it's a 1-to-1 molar ratio. If it's a 1-to-2 molar ratio, it's a little more complicated, and we'll have a look at that in a minute. But you can look up tables like this. You'll find them in the standard chemistry textbooks, examples of this. This is one table that we use from time to time at Abertay, list of solubility products, a whole series of hydroxides, oxalates, carbonates, sulfates, chromates, phosphates, etc., sulfides. You can see some of the sulfides are very insoluble, 10 to the minus 72, which is a very, very small number. That's 72 zeros before the 72 or 71 zeros before the 1.6. So we've got 5 sulfates there from that table: calcium sulfate, strontium, barium, silver and lead. And we want to find which is the least soluble. Well, the starting point is looking for the smallest number. They're all 1-to-1 ratios with the exception of the silver sulfate. And the silver sulfate's one of the largest numbers, 10 to the minus 5. So we can exclude that as being least soluble. We look at the others: 10 to the minus 5, 10 to the minus 7, 10 to the minus 8, and 10 to the minus 11 is the smallest number. So the barium sulfate is the least soluble of those sulfates. If we're wanting to find the most soluble, we could rule out the minus 7, minus 8, minus 11. We'd then have to decide between these two, and as I said, it's a bit more complicated because of the 2 silver ions. And it depends how exactly we're working it out. You may find in some books, instead of expressing it as KSP, it's expressing it as pKSP. Quite often in science we use P notation for minus log. You may have come across pH, minus the log of the hydrogen ion concentration. In the same way, pKSP is minus the log of KSP. And it makes the numbers a bit more manageable. For silver, I think that's the wrong, silver chloride, not silver sulfate. It's 9.77. That means that the log of KSP is minus 9.77. So if we want to find KSP, we have to take the anti-log, well, we have to put a minus sign in and then take the anti-log, or 10 to the power minus Kp. These two are synonymous, they're the same meaning. So depending on your calculator, if you've got a value of pKSP and you want to find out what KSP is, you either have to use that key on your calculator or this one. Often there's the shift and log button on the calculator. So 10 to the minus 9.77, which if you work out what that is, it comes out as 1.7 times 10 to the minus 10. You see that the minus 9 and the minus 10 here, the 0.77 gives us that 1.7 here. So that power should be close to the number that we've got for PKSP. So it's a check that we've actually put the numbers correctly into the calculator and hit the right buttons. It's always worth checking your answers, looking at them, seeing, is this the sort of answer I would expect? If it is, then there's a good chance you've done the calculation correctly. If it isn't, it may be that you've made a mistake, and it's worth just checking through. Basically, because PKSP is minus the log of KSP, means that if we have a big number for PKSP, it corresponds with a small number for KSP. Now, I said it's more complex comparing solubility if we've got different number of ions on both sides. If we've got something like calcium hydroxide, where we've got one calcium to two hydroxides. So we'll just have a look at some calculations. We'll start off with a straightforward one. We're saying barium sulfate was the least soluble of those 5 sulfates we were looking at. And we said KSP was 9.9 times 10 to the negative 11. It's always worth writing down a chemical equation for any problems you have to solve, just to remind yourself of the ratio of the molar quantities of the species taking part. It may be obvious to you, and you may feel comfortable missing that step out, but it can often help you to pick out possible problems that you might have where you've got different ratios. I think Keith will be doing, or has done with you, titration calculations where you end up with 1:2 ratio or 2:1 ratio. And if you don't write the equation down, it's sometimes easy to forget that there's a 1:2 ratio. So I've written down the equation here. We've got the 2 plus ion and a 2 minus ion. If we have X moles of barium sulfate dissolve, we get X moles of barium, X moles of sulfate ion. So we start off with some solid here, and a small amount of it, X, is dissolved, giving us X barium, X sulfates. 9.9 times 10 to the minus 11 is concentration of barium times concentration of sulfate, X times X, because they're in the same volume. Then just a matter, we need to solve that equation. Just realise putting X here for a multiplication and X there could look a bit confusing. One is a multiplication sign, one is the unknown. 9.9 times 10 to the negative 11 is X squared. So X is the square root of X squared. X is the square root of 9.9 times 10 to the negative 11. And if we work that out, probably too many significant figures here, 4 significant figures, whereas this is only to 2 significant figures. I could probably round that to 9.9 times 10 to the minus 6 moles per litre. So we've worked out the concentration of the barium ions and corresponding concentration of the sulfate ions. This is about half the value of that. So we found the solubility. If we wanted the solubility in grams, obviously we'd have to multiply this by the molecular mass of the barium, the gram formula weight of the barium ion, and we could work out in grams per litre. If we wanted it in grams per litre of barium sulfate, we'd have to find the gram formula weight of barium sulfate and multiply that by the number of moles, and we'd find out in grams per litre how much dissolved. Looking now at one where we've got a ratio of 2 to 1, it becomes a bit more complex. In this case, we're going to take PKSP, and from that table it's 5.10. So we can work out KSP, we'll put a minus sign before the 5.1, and then the anti-log, or 10 to that power, comes out 7.9 times 10 to the negative 6. If we get X moles of calcium hydroxide dissolving from our solid, we end up with X moles of calcium, but we end up with 2 hydroxides, so we end up with 2X moles of hydroxide. So whereas before it was X and X, here we've got X and 2X. And these are moles, but they're in the same volume, same amount of water, so the molar ratio is going to be the same proportion. If we've got X moles of one in a given volume, 2X moles of the other in a given volume, we can use these as indications of the concentration. KSP, as seen on the previous slide, is the product of the ions, calcium ion times the hydroxide ion times the hydroxide ion. So calcium times hydroxide squared. Again, we can put values in. This time, we've got X for the calcium, 2X for the hydroxide. So we have to watch out that we put the 2X in, because that 2X is squared. We end up with 4X cubed for our expression of the solubility product. We can put in the numerical value we've got. 4x cubed is 7.94 times 10 to the negative 6. Divide both sides by 4, we end up with x cubed is 1.985 times 10 to the minus 6. And then it's a matter of using the calculator to find the cube root of 1.9 times 10 to the minus 6. And we end up with a larger number than we have done previously. We've ended up with 10 to the minus 5, 10 to the minus 6. Here we've got 10 to the minus 2. And make sure when you're familiar with your calculator or computer how to do cube roots, the particular key to use or particular notation to use if you're using cube root of a number. Some of the questions in the tutorial will look at different ratios of ions, and when you've got different ratios, it affects this value here. You'll end up with a 2 or a 3 here. You may end up with a number in front of the x of the other ion as well, and you're then ending up taking a root that's not just a square root. Bear in mind that X was the concentration that we used for calcium. The OH was 2X, so the OH is going to be twice that value. So you just have to watch slightly what you're trying to calculate. If you were calculating the solubility of calcium hydroxide, it's 1-to-1 with the calcium ions. So X is the number of moles of calcium hydroxide. The solubility of calcium hydroxide is 0.01257 moles per litre calcium hydroxide. And we could work that out in grams per litre of the calcium hydroxide. It's just under 1 gram per litre of calcium hydroxide. So although we're saying it's insoluble, 1 gram per litre is a significant amount of calcium hydroxide in solution, but it's sparingly soluble. That's why I'm saying, rather than saying something's insoluble, we ought to really talk about sparingly soluble. Obviously, other materials are soluble at tens or hundreds of grams per litre. Yeah?
Can I really question that out? Like if it was an example, what would be the question? Like what would be a typical question for it?
Sorry, what would be the question in?
Like to work it out, like what would be a typical question to like do that calculation?
To do that question in the tutorial question, it would ask you something like, what is the solubility of calcium from calcium hydroxide in water? In which case, you would work out this value. If it asked what was the solubility of calcium hydroxide, you go through it, get to this point. Because it's the calcium and the calcium hydroxide are both the same number of moles, you report that as the calcium hydroxide solubility. You're probably unlikely to, or less likely to be working out the anion concentration. It's possible you might, if you wanted to work out the pH of this solution, you need to work out the number of moles per litre of hydroxide ions, and then use that value to work out the pH of the solution. So there may be differences in the way the question's worded, but does that give you some idea of the sort of thing that might be asked? Yeah. You should see in the tutorial questions the sort of things that are asked. And in the coursework, I don't think any of the questions are significantly different from the sort of questions that you've covered in the tutorials. So there may be bits of differences between them, or bits of differences in the way they're worded. There won't necessarily be exactly the same wording, but you won't be asked to do something completely different from what you've done in the tutorials. Okay, some of the questions won't necessarily be straight writing down an answer. We've done them a variety of different types of answers. Some of them you put down a number for the answer. Some of them you fill in a box with an answer. Some of them are multiple choice, where you've got 4 possible answers and you click on the one that is the right answer. So you still have to do the calculation, unless you want to take a 1 in 4 chance at guessing it. But when you've done the calculation, you click on the box. So the actual calculation is not different from what you've actually done in the tutorials. Okay? One thing that comes on from the solubility product is how we can affect solubility, and we can decrease solubility. There's a couple of ways that can be done, but the main one I'm interested in is decreasing solubility by the common ion effect. I'll put all the slides up because it's got the common ion effect at the bottom. One way of affecting solubility, as I mentioned a few minutes ago, is temperature. And as temperature goes up, solubility often goes up. And as temperature goes down, solubility goes down. So temperature has an effect because it affects the rate constants, and hence the equilibrium constant. This constant, KSP, always has to be obeyed, and it's like a seesaw. If we have more chloride ions, we're going to have less silver ions. If we've got more silver ions, less chloride ions. So one way of decreasing solubility of silver in solution, silver chloride in solution, is to increase the concentration of chloride ions. And as we do that, one side goes up, the other side goes down. And sodium chloride is a cheap soluble chloride that we can use to add to it. If we look at the equilibrium constant, we looked at that a few minutes ago and worked out the equilibrium concentration of silver ions and chloride ions in water. So if we have silver chloride and add it to water, we'll end up with 1.3 times 10 to the minus 5 moles per litre of silver ions in water. If we dissolve sodium chloride in water, and make it 0.1 molar solution in chloride ions. We put 0.1 in for the chloride. This has to be the number that makes the product 1.7 times 10 to the minus 10. So silver ions, 1.7 times 10 to the minus 9. Because we've added a common ion, we've added the same ion that's in both these compounds, the solubility of silver has decreased by a factor of 10,000. And if you're treating wastewater, there'll be a limit of the number of milligrams of silver you can discharge in your wastewater. And if you can precipitate the silver to below that level, then you can discharge the water without any further treatment. So common ion effect is one way of decreasing solubility. One way of increasing solubility is by temperature. Most things, not all, but the majority, increase in solubility as temperature increases. One notable exception is gases in water, and if you have cold tap water and let it warm up, you find little bubbles collect on the side of the glass, because air solubility in warm water is less than air solubility in cold water, and they'll tend to come out of solution. You look more at free energy for reaction. Free energy of equilibrium is at equilibrium is 0, and the free energy is given by this expression. It's dependent upon temperature. So as temperature changes, the equilibrium gets displaced. So changing temperature is one way of increasing solubility, and conversely, if we want to decrease solubility, lowering temperature can help. A second way of increasing solubility is to remove one of the products of that equilibrium, because as you keep taking away one of the products, the equilibrium gets displaced to re-establish itself. So if we've got calcium carbonate, limestone, it forms an equilibrium with calcium and carbonate ions, and that has KSP value 4.8 times 10 to the minus 9. That's always got to be obeyed. So calcium carbonate is sparingly soluble in water. It will dissolve to a small amount, and over thousands or millions of years you can get stalagmites and stalactites forming in caves as the water dissolves some of the limestone, and then it recrystallises out in the cave. If we add hydrogen ions, we displace that equilibrium a bit, because hydrogen ion can combine with a carbonate ion and form a hydrogen carbonate ion. A second hydrogen can combine with the hydrogen carbonate ion, form carbonic acid, and that carbonic acid can separate into water and carbon dioxide gas. So if we add acid to calcium carbonate, the carbonate is taken away from that equilibrium as carbon dioxide. Because the carbonate ion's removed, this equilibrium is displaced, more calcium carbonate has to dissolve, and we get more calcium in solution. So you've probably seen the fizzing when you add acid to carbonates. That's the chemical reaction that's occurring, and we're adding a strong acid to a salt of a weak acid and displacing the equilibrium, and we're increasing the solubility by taking away one of the ions from solution. It's used quite a bit in technology. If you want to dissolve precious metals like gold and platinum, we use what's called aqua regia, nitric and hydrochloric acid in a 1:3 ratio, and whereas the gold will form an equilibrium with gold ions in solution, here we're forming a complex ion with the gold, so we don't actually have gold ions in solution, we have the gold in a different chemical form, and so the gold will tend to increase in solubility because it's going right through to a different chemical form. Similarly, detergents often have sodium polyphosphate in to displace equilibrium with calcium ions in hard water areas and stop solid scum forming between the calcium ions and the detergent anions. Third possibility is diverse ion effect. Whoops. And instead of the common ion and having an ion that is present in our salt, we're taking diverse ions, a salt that doesn't have any ions in common with the salt that we're interested in. So if it was silver chloride, to reduce solubility we used sodium chloride because it had a common ion of the chloride. If we used sodium nitrate, there's no ions in common between them. We've got diverse set of ions there, and we can increase the solubility. It's not a matter of adding a small amount of sodium nitrate. You're talking about 0.1 molar solutions rather than 10 to the minus 5, 10 to the minus 6 moles per litre of the sodium nitrate. The reason this works, I said before about using the square brackets as an abbreviation for concentration. Square brackets are correct for the concentration, but really in that expression that I had for KSP, I wrote it as KSP is product of these two. It should be the activity of calcium and the activity of the hydroxide squared instead of the concentration of the ions. Now if we've got dilute solutions, which normally we're dealing with insoluble or sparingly soluble salts, the concentration and the activity are in effect the same number, so we tend to use that rather than writing the activity. The activity is two properties, fugacity times concentration, and dilute solutions, that is equal to 1. But as you get more concentrated solutions, it changes from 1, and so we affect the activity and the concentration. The concentration can therefore increase. So you can find that you can increase solubility of some salts by dissolving a different salt in the water and changing the fugacity and increasing the solubility. Oops. Different branches of science use different units for solubility. Normally in chemistry we talk about moles per litre, sometimes we talk about millimoles per litre. Often in industry or in data sources you may find solubility expressed in grams per litre. Older textbooks often express it in grams per 100 millilitres, so a factor of 10 different from grams per litre. They did that because it was a percentage weight for volume. 1 gram per 100 mils is 1% weight for volume. Sometimes if you're dealing with liquids, you work on a percentage percentage volume for volume. If you look at vinegar or alcoholic drinks, they express it percentage by volume, alcohol by volume. For very dilute solutions, we often refer to parts per million or milligrams per litre. Parts per million and milligrams per litre are effectively the same unit, and on Blackboard, these slides are on Blackboard, but just to show you them, if you're converting from one of these to one of those units, they tend to be fairly simple ratios of multiples of 10. You can see that grams per 100 mils and grams and percentage weight volume are the same thing. The parts per million and milligrams per litre are the same thing. Going here we've got a ratio of 10, here we've got a ratio of 1,000 going from here to here, but if you're working in moles, you've got to include the molecular weight in your calculation as well, but for the others that are based in mass, then it's just factors of 10. But if you have to do that, it's probably simplest doing it step by step, converting moles per litre to grams per litre, and then grams per litre to parts per million or whatever. That I think just complicates things. It's giving examples of that I think looks even worse than it is. A lot of the glassware we use for measuring volume and making up solutions tends to be made out of glass. I'm going to go through this fairly quickly because I suspect it's fairly obvious for you, and it's covered in the skills lab. We use glass because it's easy to form it to shape. We can see inside what's happening. It's fairly robust. It will break if you drop it, but you can knock things over and they won't break. And glass is chemically inert to most things. It will react with strong alkali, it will react with hydrofluoric acid. There are occasions when we don't use glass, sometimes at high temperature. We have to use something like silica. When I was doing my PhD, I was working with molten zinc, and we had to make things out of silica rather than out of glass, so we could see what was happening inside the vessel. Sometimes it may be made out of nickel or even platinum. Sometimes we use plastic, but have to be careful with plastic because it can absorb material out of solution, and it can react with organic solvents. We've got certain glassware for measuring volumes approximately. Beakers tend to be the basic tool for making up solutions. Conical flasks have the advantage of the sloping side, so avoid spillages when you're shaking or stirring the solution. Measuring cylinders for where we need to add an approximate amount of solution. And for precise volumes, accurate volumes, burettes for delivering variable amounts, pipettes for delivering fixed amounts of solution, and standard flask for giving a known volume. I think Keith is covering this as well, making some of his tutorial questions are about how much do you need to weigh out to make a solution of a known concentration. When we talk about standard solutions, a standard solution is really a solution of a known concentration, and its concentration is given by the moles divided by volume. If you're not sure of the moles, you work out the moles from the mass and the molar mass. If you like little triangles, they're the two relevant triangles. If we're making a standard solution, we need to use something which is pure and dry. Some materials tend to react with the air or absorb moisture from the air and aren't of a 100% purity. And in that case, we either have to make up a solution and standardize it against another solution, or sometimes we can buy files of material that we break open and dissolve it all in solution to make up our standard solution. Is this my last slide? No, not quite, but yeah, it's more relevant to titration reactions, which I think Keith will talk about, but if you're doing titrations, you need a reaction which is going to go 100% to the product you want, not have any side reactions, something which goes quickly, so that you're not having to wait for the reaction to be complete, and where you've got a distinctive equivalence point so you know that you've got to the to equal amounts of the equal mole amounts of the reagents. Dilution, again, you're doing that in Keith's tutorial questions and in the skills labs. It's basically calculations on the number of moles that we transfer in the pipette, and you'll have that number of moles in your standard flask, and so you can work out the concentration by moles divided by volume, and if you do that, the two steps, you end up, the new concentration is the old concentration that you had multiplied by the dilution ratio, the pipette volume to the standard flask volume. And as you be aware, you just need to choose these in an appropriate ratio, and we try to work in ratios that are going to make the calculations easier. 10 to 1 is a lot easier to work with than 40 to 100. Okay, that was a bit rushed there towards the end. My apologies for that. We'll carry on next time, starting to look at pH and acids and bases. So I'll put the next handout on Blackboard in the next day or two. Okay?
Why are you using it?